Yep, no worries. Anyway, we can talk about it more later, but I figured I'd give you an update.
Yeah, that's awesome. Yeah, I want to talk more. I'll call you back later.
Okay, sounds good.
See you.
All right.
Yes. The remaining engineers. The remaining Dynamics engineers are in the house. How's it going?
Not bad. How you doing?
Yeah, not too shabby.
Jesus Christ, this class is huge. So many students.
Yeah, is that going to be only 3 of us?
How am I going to remember all your names? Yeah, I think so. It's Dynamics is kind of an interesting class because it isn't needed by all engineering majors. So despite the fact that it always kind of ends up going in about half. So true to form. Here we are. Well, cool. Let me give you just kind of a little, just a brief understanding of kind of some of the language that kind of flies around all of this, just so you kind of understand it. Really the study of, what is your book called? Yeah, your book. Actually, speaking of books, did I send you guys an email already about getting the book?
So you did a long time ago, and on the syllabus, I think syllabus has a statics book.
Seriously? How could that possibly
I think so.
I'm sure you're not wrong. I'm just going to look really quick. I might have copied the format of that over or something. I don't know, to try to get the format right or something, and forgot about the book. But yeah, it should be the Dynamics book. It's pulling it up right now. But it should look like this on the front. That's what I sent a while ago. Yeah, you're right. The syllabus does say statics, not dynamics. So I must have copied that over and foolishly not added it on there. Did all of you get that previous email about this book? You want me to resend that? Just because I sent one that had a ISBN number and all that stuff on it, so that you get the right one. I'm hearing nothing from you.
So I got an email and I bought the book from the website that was on the screenshot. Mm-hmm. And ebook, you actually can't download it on the computer. So just keep that in mind. It's all online.
Right. Yeah, you can't download it. How much did you pay for it, Evold?
Like $45, something like that.
Yeah, awesome. That's why we're doing it this way. Much more reasonable. Cool. Yeah, so we'll be working out of that thing immediately. So anyway, just to give you kind of just a rough sense, together mechanics is statics plus dynamics, and we just studied statics. And really, statics, if you think about it, was kind of the forces required to, maybe I'll just say for equilibrium. In other words, what forces are pushing on things, or what forces do you need to add as an engineer to push on things so that they don't move? Whereas really dynamics that we're studying now are really the forces required to get things moving. So let's see, Landon and Evald were on that field trip we did last time, but we were looking at a track hoe that was there, like, you know, it had hydraulics and it was lifting dirt and moving it around and so forth. And so with respect to a building or a bridge, you want things not to move, but with respect to like a tower crane or a track hoe, like you want things moving. The whole point of it is to get things moving. And so we're really going to be studying motion in a sense. And this is where your physics knowledge will hopefully come into play. The other thing is the other couple of words that might fly around a little bit that I just want you to think about. This isn't important. This isn't going to test question by any stretch, but there's two things that you might read in the start of your book: kinematics and kinetics. And they're just words. And I find myself needing to look over at my definition that I wrote in my notes to even know what they are. It's not like you need a working definition of this. So it's not so much the words I'm interested in, but kinematics is really the geometry, kind of the geometry or geometric aspects of motion. Whereas kinetics is basically the forces that cause the motion. So when I say geometry of motion, I just mean like if a skier jumps off a jump, they're going to fly through the air in the shape of a parabola. That would be kinematics because it's flying in the shape of a parabola. But kinetics would be, oh, they skied down a hill that was 45 degrees for 100 yards and then they hit the jump. And so it's that gravitational pull on them that gave them the speed they had when they left the lip. And so that's kind of the idea. It's just like, how are they going to fly? And then what caused them to fly that way? Or a track hoe is going to, drag in, and its bucket will be kind of following the shape of a circle, but then it's the mechanism of the hydraulic rams inside it that actually cause that force to actually make that happen. And so that's the concepts. It's just what causes the motion and what shape does the motion take. Who cares what the names are, as far as my class is concerned. But you just might see that those words kind of fly around a little bit. I just want you to sort of have a working definition. Myself, I can kind of see why somebody gave a name to these things, just because, yeah, I can see that, sometimes I want stuff not to move and sometimes I want it to move. And those are very different engineering tasks. And so that somebody would think that's worth a name. Yeah, I get that. That makes sense. So anyway, today we're really studying, kinematics, the geometry of motion. So let's actually get after that and do that right now. And we're going to use some calculus to create some of the formulas that you need. And let me see if I already posted this in my open math. I'm going to unshare a screen, but there's some notes that you are going to want to have. Share. Let me see if it's already in there. I think it is. Share a screen. So I'm going into you guys, just like last term. Yeah, dynamics formulas right there. Just like last term, I'll be posting the class notes in here every day, and then there'll be test reviews in here, which there already are, and your syllabus is in here, and then these dynamics formulas. And then also just a reminder from last term too, because this is the same sheet, but I posted just a Word document of two different dudes that both talk about statics and dynamics. And structure free is awesome. We're going to get into some hard stuff later on in this class. This is my favorite. These are in order. This guy is just awesome. So he's got a whole playlist of YouTube videos. So does this Jeff Hansen guy. Real practical, straightforward explanation. So these are kind of in order of what I consider to be the most useful. So, if you want some extra input, that'd be good, because we always end up running out of time. And then these dynamics formulas, we're going to tackle these right now. So chapter 12 right here, we're going to be tackling these formulas right off the bat. And so we're going to make them really quick. So one way or another, pull that thing up right now, because I'm just going to be referring to it. But you're going to certainly have this on a test. have all of these formulas in front of you. And so this is really going to feel like physics. Physics is all these formulas that you're staring at all the time. And I'm hoping since you didn't have it that long ago, and it's a prerequisite for this, that this is not entirely new to you. So let's make these, because I think it's, in a physics class, you tend to just be given these, but now that you know some calculus, you're in a position to make these for yourself in a way that maybe kind of the average person can't. And so let's see if we can make a little progress with that right now. Resharing the screen. Come on, man. So there's really three, I don't know, characteristics or aspects of motion. You might think of something like a human. What is a human? What aspects does a human have, or what characteristics do they have? And it's like height and gender and personality, and there's all kinds of things. Humans are much more complicated, but really motion really has three components. Do you already know what they are? I don't know if you do or not.
Is that like translation, rotation, and some third one? I don't know.
Yeah, that is, the answer to that could be yes, depending on how you look at it. I'm thinking of something a little bit different. What you're talking about is like if a human was flying through the air, they could sort of move, they could also twist, and they could also rotate. And so twisting and rotating are really kind of the same thing. That's true. I'm thinking of it more as like the motion of a particle, in the end, like the center of mass of that person.
So X, Y, Z.
Yeah. So I guess I'm asking you to read my mind here a little bit, but really I'm talking about position, like where is it? And velocity, how fast is it going? And acceleration, which is it speeding up? And in a sense, Daniel, your answer about X, Y, and Z would be like aspects of position. In other words, if you want to describe their position, it would take those three components to describe where it was relative to some point. But really, we're talking about position, velocity, and acceleration. And so the formula sheet that I gave you has a list of those things. But I want to know if this statement makes some sense to you. Does this make some sense to you from your calculus knowledge? Can you read that statement beyond just reading the letters? What is calculus?
Velocity is the change in position over the change in time, and then the acceleration is like the change of velocity over time.
That's exactly right. So I don't know why, but S is always used for position. Seems like it might be P or something like that, but all of these things are relative to time. That's exactly right. And so that's what velocity is change of position over time. And so that's a derivative statement. And acceleration is when you change your velocity. So acceleration would be the change of velocity over time. And so that turns out to be really powerful. And I'll show you what I mean by that in just a second. Well, let's even do some of it right now. So like, what can I do with that? In a sense, those are just definitions written in a calculus way, but if you change your velocity, that's what we call acceleration. Of course, if you're driving the car, that's one of your options. You usually get in the car because you're trying to change positions, but then you get there by picking a velocity, and then you even change that velocity as you're going along. And so I guess it's important that you understand conceptually that this would be the three things that would concern something moving. Going to change position, it could change velocity, and it could change acceleration. But let's just think about what calculus would say about some of these things and just play around with them a little bit. Like this statement right here. Would you agree if I multiplied both sides by dt? I'd get that statement. And now, what happens if you integrate, take an integral of that statement? That's where you've seen dt and dv before. So if I integrated both sides and said, what is the integral of a with respect to t? And what is the integral of nothing? Well, the integral of 1. There's a 1 in there, I guess you could say. But if you take the integral of a, thinking of a as a constant, and I guess I need to point that out, or at least I need to. If I take the integral of a constant, if that's like the integral of 5 with respect to t, doesn't it just grow a t, if you will? And then technically there's like a constant added on to that. And if you take the integral of 1 with respect to v, doesn't it just kind of grow a v? And so we just made one of these equations. And so if you think of this v equals a t plus c, does it make sense that I could even write it as this is the velocity and just kind of point out, hey, that's a function of time? In other words, you have to know what time it is to know what the velocity is. And does it make sense at t0, at t equals 0, then that c value would be the initial velocity? Like that's what it would mean. Since if I put t as 0 into here, I get nothing. And so that means b of 0, v at time 0 is c. So time 0 is the initial. So that c is really initial velocity. And maybe you've seen from physics that sometimes instead of just calling that some random c, their little o down there, that little 0 kind of stands for initial velocity. So it's still just a constant. But now you're understanding that isn't just some random constant, that's actually the initial velocity of something. And so ultimately this equation, I'm going to rewrite it without the t in there. Ultimately, this equation is one very powerful equation. And if you think about it, just stop and think about it, it actually makes all kinds of sense. In other words, if I started out at like 10 miles per hour, and then I accelerated 2 miles per hour, then 1 hour later, wouldn't I be going 12? I mean, I'm really taking whatever my acceleration is. If my acceleration was 2 and I started out at 10, then 1 hour later, I'd be adding 1 2 to my 10. 2 hours later, I'd be adding 2 2s to my 10, and I'd be at 14. Notice that formula makes sense. It's actually calculus that gives us that formula. You would have been given this in physics, but probably not had any sense of where it came from. So that's a classic velocity equation. And the way you need to look at this stuff in terms of your algebra understanding and in terms of how this class works is like a recipe. In other words, this is a velocity recipe. If you want to know the velocity, then you're going to have to know, well, 3 things. This recipe calls for 3 ingredients. You're going to have to know how fast you're going when you started. You're going to have to know if you're accelerating. You could be not accelerating at all. And then how much time has passed. You're going to have to know all 3 of those things if you'd like to know your velocity at any particular time. A recipe with 3 ingredients. But now, let's continue with the second one of these, which is, isn't it also true, using the same logic, that v times dt would be equal to ds? And so if I integrated those again, so that I have the integral of v with respect to t, which I need to write as dt, the integral of v with respect to t equals the integral of ds, doesn't that integral of v, if you will, grow a t? And that 1, the integral of 1 with respect to s, would grow an s. And I didn't kind of highlight this on the first one, but does it make sense that this would really, both of these would actually have constants added to them in terms of your calculus understanding? So it'd be like constant 1 and constant 2. But does it make sense I could kind of subtract this to the other side so there's only one constant? That's kind of what I did before. I just didn't notice that I didn't point that out. And even better, what if we did this instead? What if before we even took the integral of v, we replaced v with what we just figured out it was equal to, which was at plus v0. Then with respect to t, at, don't you add 1 to the exponent? It's t to the 1 right now, so wouldn't it become at to the 2 and then divided by 2 or times a half? And doesn't that initial velocity grow a t, and then there's plus a constant here? So there's our position equation. So again, these should not look entirely new to you. You should find yourself thinking, oh yeah, I remember seeing those. So our second kind of powerful equation, our second recipe is, if you want to know what your position is, well, your position would depend on all kinds of things. It would depend on your velocity, it would depend on the time, and it would also depend on where you started. Notice for the same reason as a second ago, if the time was 0, these two terms would cancel out. And so at time 0, this constant would be your initial position. So ultimately then our equation says 1/2 at squared plus v0, initial velocity of t plus position 0. Okay, so that's kind of our big takeaway. So these are a couple of the notes on your note sheet. Now again, you don't have to make these. I just think it's kind of cool. It's kind of cool to be able to make them since you've had some calculus, since you know a little bit more than you did when you maybe first took physics. And I don't know if you took it from Dusty, I don't know if he showed you this stuff, but notice on your note sheet, I just showed you kind of all the first formulas. What's your thoughts on that? You're kind of like, okay, no problem, let's go. Or questions, you taking it in, where are we at?
I think probably we should look at the problem.
Yeah, in other words, let's use it for something.
Yeah.
Yeah, I think that makes sense. And you may notice on my note sheet too, there's a couple of other equations that were made. I don't think I'll maybe talk about those because I'm afraid I'm going to be out of time, but let's use this. And I think that integral concept is really important, and it's important for some of these problems. And so maybe we'll come back to this, but let's do a problem. So I'm going to go get our first example. So this is a little annoying, and this is what makes it sound like a physics problem, but it says a particle moves along a straight. There's a lot about this problem that's incredibly dumb, in my opinion. So keep in mind, though, it's like if this is a deer running, it's like the deer's center of mass is how the deer can be described. So imagine like a X Games guy jumping over a jump. Well, he's flipping through the air, and he can do anything he wants, flipping and twisting, but his center of mass is just going to fly through the air like a parabola. Does that make sense? So it's like two separate things going on. And so it's okay to call something a particle. The other thing that's kind of dumb about this is this particle moves along a straight line. So notice we're given, you're basically, what these problems come down to is because of the three aspects of motion, position, velocity, and acceleration, We got to know something. But if we know one thing, then we know everything. So notice this time we're given position. So its position is defined by a parabola. But rather than read ahead, why don't you just slow down a little bit and let's just think about this for a second. So for instance, if I said, I'm going to make a little chart over here of time and position. And so at time 0, all I'm doing is plugging 0 into that formula. If I plug 0 in for t, then I get 5. So this thing is at position 5. And notice it's 5 meters, whatever that's matter. So it's 5 meters from something. And then at time 1, I put 1 in there. 1 squared minus 1 plus 5. I end up with, what do I get for that? Nothing? 0? I get nothing for that. So it went from 5 to 0. So let's see, what is that saying? So out here at 5, it was here at time 0. And then it went, now it's here at time 1, right? Isn't that what it's saying? Like, just go slow. This is not complicated. It looks complicated if you try to kind of cheat your way through this quickly, but it's not complicated if you just slow down a little bit and like draw it out. This isn't hard. We're in a room. So let's see what happens at time 2 then. 2 seconds later, I put 2 into that and I get -3 out. So it apparently continues to the left. And now it's at -3. Oops, let's draw that down here. And then I stick a 3 in. We're only concerned to 6 seconds, thankfully. We're going to be here forever. First of all, what do you notice about its speed? Like it went from 5 to 0 and then from 0 to -3. Is this particle or is this skateboarder or whatever increasing speed or decreasing?
Decreasing.
Would you say?
Decreasing.
That's right, because it went 5 meters in the first second, but then it only went 3 meters in the next second. So it's actually slowing down. And the negative just says it's going left. So when I stick 3 in, I get -4, which means it's even slowing down more. It's almost like it's coming to a stop. And so at time 3, there it is. And then at time 4, crazily enough, it's at -3 again. Oh, that's weird. That means it turned around. It's like it turned around and went back the other direction so that at time 4, it's actually here. So it's actually going, and it said it's straight line motion. So that means it actually reached the end, turned around, and just came straight back again. That's kind of weird. So this isn't like a bird flying through the air. And then at time 5, I throw a 5 in there and I get 0, which means it sort of got back to here again at time 5. And then I put 6 in and it's actually right back at 5 again. And so times 6. So basically it sort of went from 5 to -4. So it's like it went left 9 and then it went back right 9, but it was changing speeds the whole time. Does that make sense? You see, I can just see that stuff without any formulas, just by drawing a picture and so forth. So all I did really was just understand the first sentence. For all I know, after this, it's going to say, what's your favorite color? And I wasted all this time. But most people read the problem and then proceed to, I don't know what to do too quickly. Like make sure you actually understand the question. So its position is defined by that. Notice I understand a lot that I didn't understand a minute ago. I really kind of feel like I have a sense of what this thing is doing now. It's just kind of flying along. Interesting. But then what do they ask me? Okay, so determine the average velocity, the average speed. Wait, speed, velocity? Is it speed and velocity the same thing? Do you know this from physics?
Of what?
Go ahead, Landon.
Yeah, the difference between speed and
You're chopped up. Maybe you're.
yeah, sorry, I'm kind of on a bad connection.
Oh, I heard that part. Try it again. Try it one more time.
Okay.
Yeah, you're good now.
Velocity implies direction, whereas speed
Yeah, speed doesn't care about direction. but velocity, I'm sorry, speed cares about direction, but velocity doesn't. Technically, velocity equals the change of s over the change of time, like I just said a second ago, ds dt. Well, notice in the change of time from 0 to 6 seconds, you actually went from 5 to 5, like you went nowhere. So the velocity of this is actually 0 meters a second velocity, because you didn't go anywhere in those 6 seconds. Whereas speed, the slightly technical difference, is change of, well, I don't know what you want to say, maybe change of distance over time, something like that. Well, how far did this particle travel in that 6 seconds? Didn't it go all the way down? Oops, that wasn't the right tool. Didn't it go all the way from 5 to -4, which is actually a distance of 9? So it actually went 9 that way and then 9 back this way. Didn't it go a total of 18? Notice also it said the average velocity and the average speed. It didn't say the speed at 6 seconds. It's the average speed. So that's why I didn't need a formula to figure that out. So that's kind of tricky. There is a difference between speed and velocity, kind of a technicality, if you will. Now, let's just play around with derivatives a little bit. If s equals t squared minus 6t plus 5, and we said earlier that ds dt is equal to velocity, then if you want the velocity, you got to take the derivative of that. Well, isn't ds dt, which is velocity then, isn't the derivative of t squared 2t, and isn't the derivative of -6t -6? So there's your velocity equation. So that's kind of cool. We have this equation that tells us our velocity at any point. So in these two answers up here, we had the average, and that's fine for the entire 6 seconds. But this velocity formula allows us to find the velocity at any time we want. Like, for instance, let's go fill this chart in a little more. What's your velocity at time 0? Well, according to this formula right here, if I put in t0, I get -6. That's your velocity. Does that make sense? Why would it be negative? Well, he's going left. That makes sense. But didn't he travel 5 feet in 1 second? Wouldn't you think this would be 5? Didn't he travel 5 in that first second, not 6? Can you reconcile that? Well, he's not going the same speed. Does it make sense? We already agreed he's slowing down. So if he was going 5 in that first second, he'd be slowing down. And so if he was going 5, he wouldn't have made it to 5 in 1 second. Does that make sense? But if he's going 6 and he's slowing down, then maybe he would make it to 5 because he's slowing down the whole time. So it actually would have to be bigger than 5 since he went 5 meters in his first second. So thankfully for this formula, I can figure that out. If I stick 1 into that formula, I get -4. So his speed went down to -4. And remember, that's exactly at time 1 second. And it's only that speed for just the tenth of a second there. It's not for the entire second. If I keep going and I put in 2 times 2 is 4 minus 6. Notice I get this pattern. What do you notice about his speed? How is his speed changing? was -6, then it was -4, and then it was -2. What's happening to his velocity? His velocity is changing. He's changing his velocity, so he has an acceleration. What is it?
Two meters per second squared.
Yeah, notice he's increasing 2. If you add 2, so every time it's like +2, +2, +2, +2. So his acceleration, no matter where he is just +2 every single time, because every second he's going 2 faster than he was before. And again, velocity cares about left and right. Speed does not. So velocity thinks left and right matters. So whereas speed doesn't care, he just went 9 to 9. He went 18 total. He traveled 18 total meters. Who cares what direction? Who cares if it was 9 left and 9 right? Velocity cares. That's why we got 0 for his average velocity. So notice his acceleration is just 2. But do you notice that we see that in the chart? But couldn't we come over here and say that, well, isn't dv, isn't the change of velocity over time equal to acceleration? And so if I take the derivative of this v equation, isn't the derivative of 2t2? So it's like, yeah, of course it's 2. Like the calculus would have told me this was 2 without ever even making the chart. That's kind of cool. So notice these speeds are kind of the instantaneous speeds, the speed at every instant. The main takeaway from this, and we'll do another example, is just that if you're given one equation, that kind of gives you access to the motion, I could be given the velocity equation or an acceleration equation or a position equation, and thanks to derivatives and integrals, I can go whatever direction I want. So one thing that's really important that you understand from calculus is that if you go from, and this is what we just did, if we go from speed to velocity to acceleration, we're taking derivatives to move in that direction. The change of s is velocity. But if we're given an equation that starts with acceleration, then we're actually taking integrals to go the other direction. Does that make sense? Let's take a look at an example like that. So there's 3 aspects to motion, but fortunately they're all related to each other thanks to calculus. So I don't have to be given a separate equation for each type of motion. I can just be given one and I get the other ones for free thanks to a little bit of calculus. So let's take a look at this question. Notice what we're given this time. This time we're given an acceleration equation. And as Daniel pointed out a minute ago, notice the units of that are meters per second per second. So we increased speed 2 meters a second every second a minute ago. So it's kind of a terrible way to say it, meters per second squared, but that's just because it's meters per second. And it's a cleaner, faster way to write it is meters per second squared, but meters per second squared doesn't really mean anything. It sounds confusing when you say it that way. So does it make sense we're just given access to the motion this time in a completely different format? Now it's acceleration. So again, I find myself thinking, well, I don't know, let's just take a second and kind of make sense of this. So at time 0, maybe this will end up scoot it over. At time 0, let's see, 2 times 0 is 0, I get -1. So my acceleration is -1. At 1, I get an acceleration of 1. At 2, I get an acceleration of 3. At 3, 3 times 2 is 6, minus 1 is 5. And so, cool. So actually, I guess at first I was slowing down. I slowed my velocity down by 1. And then 1 second later, I started speeding it up by 1, then up by 3, then up by 5. And I think I see a pattern. It's like +2, +2, +2. So I can sort of tell the next one would be 7. So, okay, so the acceleration is not constant this time. It depends, the acceleration depends on what time it is. So I've just made sense of the first sentence. I don't even know what the question is asking. So how do I get from acceleration to velocity? Well, you got to take an integral. So you could do this from scratch. You could say A, we said, is the same as dv dt. That's what acceleration is the change of velocity with respect to time. And according to our formula up there, that's 2t minus 1. And then if I multiply both sides by dt, and then take the integral, because I don't really want dv's and dt's, I want v's and t's. Well, the integral of 1 with respect to v would be v. The integral of 2t would be t squared. The integral of 1 would be t. And then there's plus a constant here. Again, there's technically plus a constant on both sides. But again, do you see what just happened? I mean, to go from acceleration to velocity, you take an integral. You could just take an integral, but you can also do it by just writing these formulas out, replacing a with what a is equal to in terms of v. I replaced a with what it's equal to, dv dt. It's just the change of velocity over time. And then I said, oh, it's got v's, dv's, and dt's. Well, how do I get rid of those? I take integrals. How am I supposed to know what this constant is, though? Because if I'm going to use this for something, that can't just be some random constant. Do you notice up here in the problem, they gave us some initial conditions? In other words, they told us what happens. You know, if I said, hey, a guy's going to dive off a cliff, how long is it going to take him to hit the water? Does it make sense you'd have to know how tall the cliff was? I mean, that's kind of what's going on here. They're basically saying, okay, great, you got the velocity. Well, you can't get this unless you know some things initially. And the t equals 0 is why I said initial. So notice the initial velocity is apparently 2. So if I stick 0 in here for time, then I'm supposed to get 2 out for velocity. Well, that's not going to happen unless c is 2. So now I have my velocity equation, t squared minus t plus 2. So I made my velocity equation. So notice when you're going integral direction, you've actually got to be given some initial conditions. And so those constants that we left off in integration back when we took calculus are suddenly really important. So now I can actually answer a whole bunch of velocity questions. Isn't that kind of fun? I don't know if I need to do this, but I'm just kind of thinking it seems like fun. So velocity, when I put in 0 into my equation, I get 2. When I put in 1, I also get 2. That's kind of interesting. So it's like it didn't change velocity in that first second. When I put 2 in, I get 4 minus 2, which is 2 plus 2 is 4. So now it's actually speeding up, apparently. I hope I'm not calculating this wrong. Is that right? 4. That's right. When I put 3 in, 9 minus 3 is 6 plus 2 is 8. When I put 4 in, 16 minus 4 is 12 plus 2 is 14. So notice its velocity. I now know its velocity at all these different times. And I now read the problem. It says when time is 6, which sort of makes me feel like I should have went a little further with these. Maybe I'll do that really quick. Interesting by pattern, plus 0, plus 2, plus 4, plus 6. I bet the next one is plus 8. And I bet the next one is plus 10, just by pattern. But I could go back and plug those numbers in and see if that was true. This one was up 2, up 2. So anyway, I have all the way out to 6 now since I finally read the question. Notice it said determine the particle's velocity and position when t is 6 seconds. I just found the particle's velocity thanks to this equation right here. So Now that I have an equation for it, v of 6 is 32. And in this class, of course, you should be saying, let's see, what were the measurements? It was meters and seconds. So it's not feet per second, meters per second. Don't leave me the awkward problem on a test of deciding whether to take points off because you didn't label it. So now that I have this velocity equation, this time it wasn't like an average velocity, just what is the velocity? So I figured that out. Cool. And now I'm going to do the same thing again. If I know that velocity is equal to ds dt, the change of position over time, I can replace v with s, in other words. And that I just figured out that was t squared minus t plus 2, then couldn't I multiply both sides by dt so that all there are is t's on the right side and all there are is s's on the left side? And then if I take the integral of both sides with respect to t's and s's, again, there's a 1 over here. So the integral of 1 with respect to s would grow in s. T squared would become t cubed, but then I would divide by 3. T would become t squared, but then I'd have to divide by 2. 2 would grow a t, and then I'd have plus a constant here, which again, that constant technically would be the initial position. So again, where you are depends on where you started, right? I can't just say where, you can't figure out where you are unless you know where you started from. Notice this is a rather complicated formula. But again, I look at the initial conditions up there and I'm told at time 0 that my position was 1 meter. So that's how I'm going to figure this out. If I put 0 in there, I'm supposed to get 1. So I'm supposed to get a 1 out when I put 0 in. Thank God it was 0 for time. If it had been like 3 seconds for time, I'd have a lot of thinking to do, but that basically just means, sweet, S0 must be 1 then. So now I have a position equation. Question is, can you speak the language of calculus well enough to kind of track with this? So what did I really do? I started with an acceleration equation, and then by taking integrals, I created a velocity equation, and I created a position equation. And so now I can know anything I want. What did they ask? They said, what's the position after 6 seconds? In other words, what's S of 6? If I throw 6 into that mess and crunch it, times 6, I get 67 meters. How's your brain? If these are the 3 important aspects to motion, position, velocity, and acceleration, calculus allows me to bounce back and forth so that all I really need is one of the equations and I can know all the other ones. That's really cool. But these are very sterile, right? Like why would your acceleration be, 2t minus 1? Notice they're just making that up like it's some algebra formula or something. Have we answered everything that was asked? To determine the particle's velocity and position when t equals 6, I guess not. Also determine the total distance the particle travels during this time. The total distance the particle travels, isn't that just 67? Isn't that like the same question twice? What are your thoughts on that? Well, again, let's slow down a little bit. If I go back up here to kind of make a chart of what happened and I say, okay, well, great, let's add the position to this. At time 0, if I put 0 into that red equation, I get 1. Oh yeah, that, of course I did, right? Because they said the position was at 1. Oh, okay, it's kind of a trick question. See, we didn't start at 0. So I'm at mile marker 67 That's what this position equation just told us. You're at mile marker 67, but you actually started at mile marker 1. Does that make sense? So there is a different answer to this. So that's kind of a trick question. So it is good to think of this as like mile markers, or that you're traveling on a number line, so to speak. Mile markers makes it sound realistic. Number line makes it sound stupid and irrelevant. But so if it traveled from 1 to 67, then okay, then I guess the total distance traveled, because you're kind of going S of 6 minus S of 0, 67 minus 1. So you actually traveled 66 meters. Okay, so I guess there is an answer to that. So these can be tremendously confusing if you just don't slow down and kind of draw pictures of this. I think it's a good idea to even kind of go back in here and, you know, fill all of these out, fill the whole thing out, you know, fill the whole chart out, know exactly where you were at every second. I'm going to get some big ugly decimals for this statement, but I could, you know, get them on my graphing calculator without too much trouble. What's your thoughts on that? How much pain are you in right now? I want to hear from everybody.
And I mean, we can graph this, right? In decimals.
Yeah, surely. Mm-hmm.
It's not that bad. It's just like flashbacks to all those practical applications of calculus back in the day.
Mm-hmm. That's well said. So just for the fun of it, I went into just to write it all down, I went into the table. I'll just show you this quickly, but I made a table for the position equation, so I didn't have to work so hard at figuring out all the answers to the position. But just to write them in here, I'm going to round these off just so that there doesn't take so much time, but this is like 5.7 and then 11.5, and then it's out to 22.3, and then it's out to 40.2. I just like to stare at this because I got to make sure I see this as simple. So I started at mile marker 1, then I was at mile marker 2.8, and then I was at 5.7, 11.5. Can you see the acceleration there? It's like, wow, the first one, I only made like 1.8 miles of progress, but then I made 2.9 miles of progress, and then I made almost 6, and then I made like 11, and then I made 18, and then I made 27. So it's like, yeah, I'm definitely accelerating. And I look over here and I see, yeah, those accelerations are positive. It's really accelerating largely, and I can see the velocities going up, 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 up. And so it all kind of agrees. It doesn't mean I can, you know, stare at it and see, I can automatically just see that 5.8 and 11.5 make sense. It's just that overall, yeah, I'm progressing down the road through these mile markers, and my velocity is picking up pace, which I see happening over here in my position because the change is so large. Cool. So derivatives, integrals. So those two examples all together are really kind of dealing with something I should add up here, which is linear motion. In other words, the person's not traveling along a parabola. This is very oversimplified. It's not super common that people are actually traveling on a line. Our first example, they traveled along the line and then turned around and came back again. But just make sure you think about that. Thanks, Landon. Landon's out. This guy's having some computer problems that are massive. Now, so really that's a couple of questions that I think will help you be successful in 12.2. So you've got everything you need for 12.2's assignment just from those two examples, I think. Let's see, how much time do we have? I better go look at one more example just to make sure we don't run out of time. There's some other thing I want to show you, but let's just make sure we don't run out of time. So let's do one more example. And this jumps into 12.3. What's different about 12.3? So this is my own homemade problem, which is a little bit more interesting than maybe a typical question. But this deals with, the only change here is erratic motion. Erratic means it's not always by a pattern. Like every one of these, there was like an equation that modeled it. And not only that, somebody gave us a random equation from nowhere. Notice here, what you're getting is actually a graph of velocity versus time. The V of t graph. Notice, slow down again. This is the time in seconds. So 5, 10, 15, 20, all the way out to 60 seconds. Notice the jump isn't even, like it goes 5, 5, 5, and 5, and then 10, 30. So this isn't drawn to scale, just to kind of get it all to squeeze on one page, which is going to make it look a little weird potentially. And then these are velocities. And so this is 10 feet per second, 20 feet per second. And there were only 2 real velocities. Now, the first thing I'd like to ask you is, can you agree with this statement? This is the graph of a mountain biker who begins riding on a flat trail, then descends downhill. Why would that graph make sense? Why would his velocity do that? Why would his velocity go up and then stay at 10 and then go up and then stay at 20? Why would his velocity do that?
He'll have a steady velocity on the flat ground, and then he'll have a steady, faster velocity going downhill.
Yeah, basically here he would have, because he starts out on a flat trail. If he starts, he's riding at nothing, and then he starts pedaling. And so if he starts pedaling, isn't this what happens when you're a bike or in a car? You pedal, pedal, pedal. And then 5 seconds later, he kind of reaches 10 feet per second. And that's as fast as he can pedal, or as fast as he wants to pedal. And then he just kind of hangs out there for a bit. Does that concept make sense? So he's hanging out there for a bit. So now he's still pedaling. He hasn't reached the downhill yet. Do you see that? He increased his speed. He reached 10 feet per second, and then he just kept pedaling that. So the next 15 seconds, he was just pedal, 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 kind of at a constant speed going down the road. But then he got to a hill, and that hill now started to kick in, and the hill picked his speed up from 10 to 20. And notice it did that in a span of 10 seconds. It took 10 seconds to get it from 10 to 20. And then he just stayed at 20. So maybe the hill was just steep enough that it picked his speed up, but then he sort of got to a constant speed because of friction and just stayed at 20 for the next 30 seconds, was just going 20 feet per second. Anyway, that doesn't matter, but basically, again, this is like the problem before, except for the problem here is there's really like 4 phases to his motion. That's why it's called erratic, because he's changing the program. So we just did problems where there was only like 1 phase. The same thing was happening for the entire 6 seconds. Whereas here we have like a problem from 0 to 5, and then we have a problem from 5 to 20, and then from 20 to 30, and then from 30 to 60. There's like 4 different things going on. Do you see the logic in that? That's why it's called erratic, because in the real world, you could change your mind and like do something else. You could do something patternistic for the first hour and then follow some totally different pattern for the next hour. So let's see if we can tackle all these. Well, let's first consider what happens from 0. First phase, I'll put a little 1 in there. While the time works its way from 0 to 5. So we can only consider what's happening there. Well, we know something about velocity. That's what we know. But, well, the velocity is changing. Like the velocity actually goes from 0 to 10. So again, we're after what we're always after, which is an acceleration of velocity in a position equation. How do I get those? Like, which one do I get first? Do I get acceleration first? Do I get position first? Do I get velocity first? It's not obvious, I don't think. All I really know is that he linearly, notice that this is not like curved or something like that. He worked his way from 0 to 10 linearly. So it's kind of at a constant increase. Would you agree? This is the point 5, 10, and this is the point 0, 0. So I'll just ask you this question. What's the slope of that line?
2.
2. 10 minus 0 over 5 minus 0, which is actually 2. What's the meaning of that here?
It means that he's accelerating at 2 meters per second squared,
That's exactly right.
or 2 meters per second per second.
Yeah, that's exactly right. Because notice the 10 minus 0, those are speeds, aren't they? Isn't 10, isn't the y coordinate, since this is a velocity graph, isn't this meters per second? And the 5 minus 0, isn't that seconds? And so our answer to this is actually 2, but it's 2 meters per second, or 2 meters per second squared. And so that's actually the acceleration. The slope from calculus isn't the rate of change the change of something? I mean, isn't that the change of velocity? So our slope here is the change of velocity, which is actually an acceleration. So we increased speed 2 meters per second. So in a sense, that just happened to be a label. The only reason I did this is because I was thinking, isn't y equals mx plus b? I mean, I was just thinking, isn't this an equation of a line? And so I was trying to find the equation of that line, and I was thinking from algebra, I need the slope of that line. It's just that the slope actually has meaning here. So I was after velocity, and I now know that the speed is 2, or the rate of change is 2. And then what's its initial speed? What speed did it start at? Since velocity, remember, is acceleration times time plus initial velocity. What was its initial velocity? There you are. At time 0, this is a velocity graph. Its velocity was 0. So there is no velocity. So now I have my velocity equation, 2 times time. And again, let's just check and make sure that works. That means at 0 seconds, the velocity would be 0. At 1 second, it'd be 2. 2 seconds, it'd be 4. 3, it'd be 6. 4, it'd be 8. 5, it'd be 10. Yeah, that makes sense. That's increasing linearly. Couldn't I have also taken the integral of a? Like, I'm not going to do this, but couldn't I have taken the calculus approach to this and said, well, isn't a equal to ds dt? And if that's equal to 2, then couldn't I take the integral of both sides, and wouldn't the integral of 2 become 2t? This time I was just using the fact that I already did the integral and it created this equation, so I'm just going to use it. So since I happened to figure out the acceleration was 2, then I said, oh, cool, that means it's 2t. But that's how you find the equation of a line in this case. In this case, it was a line, so we got kind of lucky. Again, I could take the integral of that, or I could just steal. Couldn't I just steal the equation? Didn't we say s was equal to 1/2 at squared plus v0 times t plus position 0? Can I just steal that equation? I already made that if I want to. So again, I could come back over here if I wanted to and just start over and say, well, doesn't this mean that 2t is equal to ds dt, since velocity is ds dt, and then I could multiply dt to the other side and take an integral? Yep, you can just take integrals and derivatives every time and you don't need any equations. Or you can steal the equations that are on my sheet. I'm going to steal it this time. And so then I say, okay, cool. Well, didn't we find a was 2? And didn't we find the initial velocity was actually nothing? What about initial position? Do we know anything about initial position?
We don't, so we can just say it's 0 because we're the ones who are defining it.
You're correct. And I did take that confusion away by saying we started at 0 up here in the original problem. In other words, and what Daniel says is exactly right. You know, if you think of initial position as a mile marker, I mean, you can't be at 0, but you can always just say, well, where I started, I'm calling that 0. So I like the way you worded that, Daniel. Awesome. So cool. If that's the case, 1/2 times 2 is 1. So I get s equals t squared. And so now I have an equation that will allow me to know anything I want to know about that first phase of time from 0 to 5. I know anything I want to know. So notice one of the things that's really cool about this is you only had some information about velocity, and that's not uncommon. Like if you have a speedometer on a bike, you might know how fast you're going at any given time, but you don't have an odometer telling you what distance you're at. And so we're going to recreate all of that. So the acceleration during that time was constantly 2. The graph told us the velocities. And now I'm in a position to, well, know position. So what is S? This is really important. What is S at 5 seconds? If I throw 5 in there for time, 5 squared is 25, I get 25 feet. So in that first 5 seconds, the rider made it 25 feet. So I kind of know everything about what happened then during that first 5 seconds. And if that's all it was, then I'd be done. This is just like the previous problems we did. But now we're saying, okay, well, now things change. You tell me what's going to change. What changes in this next graph? What's different? I mean, I know it's flat, but what does that actually mean? What does it mean if it's flat cruising along here? Now we're in this section right here.
It means that the position is changing at a constant rate. So instead of being a parabola, it'll just be a line with a slope of 10.
Yeah, notice the velocity is not increasing its way up to 10. It's just staying 10, 10, 10, 10, 10, 10, 10 the entire time. So if the velocity just stays at 10 the whole time, then what's the acceleration?
Zero.
It's not increasing its speed at all. So its acceleration is 0 in that second phase. And so that's interesting. That's what's changed. Initially, the person was accelerating 2 feet per second every second because they were pedaling faster and faster and faster. And then they said, all right, that's as fast as I'm going to pedal. I'm just going to stay there at 10, which means and that's why it's called erratic, because now you just did something different. From 5 to 20, you did something completely different. So let's go take a look at that. So second phase from 5 seconds to 20 seconds, you could observe that the acceleration is equal to 0, no acceleration at all. And without doing any math. And you could also say the velocity is just 10 every single time. I don't have to do that much. It's 10, 10, 10, 10, 10 the entire time. So position, again, you have a choice. You could take the integral of that 10 and build it for yourself. Or you could just use the position equation. I don't know which one makes more sense to you. I think I'll just build it this time. I'm going to say, okay, well, if that's what V is, and V is equal to ds dt, which I know is 10, then I'll just build it for myself. So hence, I would have ds on this side. I would multiply the dt over to this side. I would take the integral. The integral of 1 with respect to s is s. The integral of 10 becomes 10t, and then it's plus an initial position. Wait a minute, you might think. I thought the equation was 1/2 AT squared plus V0T plus S of 0. Would we get the same answer if we just cheated and used that formula?
Yeah.
You would, because isn't A equal to 0, which takes that whole part out of the formula. And then initial velocity, well, that might be a little tricky. I thought the initial velocity was 0. But remember, where are we? We're in the 5 to 20 second phase. So in that phase, the initial velocity there at 5 seconds was 10. So that indeed is 10. So you end up with 10t plus the initial position. Now, very important, what's the initial position? Again, in the 5 to 20 range, what's the initial position? That's where this comes in. So the final position in the 0 to 5 range becomes the initial position in the next range. So in other words, I need, let me see, I don't want to say this. I want to write something that's not true here, and I want to see if you can figure it out. Like, isn't that what I do here? The initial position, I throw in 25.
If you have the second bit start as like a new 0, but since you already defined the base of like the parabolic section is 0, then like if you were just plugging this line in a calculator, it wouldn't perfectly line up as like continuous.
Yeah, it looks like it would work, but what Daniel said is exactly right. Like, this is not based on the same starting point. Like, we're in this new phase. Well, notice we figured out that S of 5 equals 25, right? Well, does that work down here? Does S of 5 equal 25? Question mark. The answer is no. S of 5 here would be equal to 5 times 10 is 50 plus 20 would be 75. Like, that formula would say you're going 75 feet per second at 5 seconds. You can't just immediately jump from 25 meters a second when you're, if you will, like right here, if you're just on the hair on the left side of that, and then suddenly you're going 75 a bunch later. So this initial position thing is a little tricky when you have erratic motion, because you can't just say, oh, throw a 25 on the end of that. What you have to say is, you have to say that yeah, S equals 10t plus the initial position, but I need that to be 25. Does that make sense? I need it to be 25. And so your initial position, you got to solve for that. It's not quite as obvious as you might think. And so if I throw 5 in here, then I end up with 5 times 10 is 50. I need 50 plus the initial position to be 25. That means the initial position would have to be negative 25. So my position equation during this period of time is actually 10t minus 25. It's very tricky. And so that allows it to pick up where it left off. So now when I stick 5 in, I really do get 25. And then I can stick 6 and 7 and 8 and 9 and 10 and all the numbers that take me up to 20. And maybe while I'm here, I'll point that out. Like, so I'm cruising along. And so where do I end? What's kind of my final position for this time frame? And I'm going to include that in here between 20 and 5. What's my final position for that? Well, that would happen at S of 20. If I stick 20 in, 20 times 10 is 200, minus 25 is 175. So basically after 20 seconds, I'm at 175 meters. That's how far I've ridden that bike. So apparently 25 meters in the first 5 seconds, and then 150 meters in the next 15 seconds from 5 to 20. So let's look at the third phase where this thing is increasing speed again. The third phase of the erratic motion. So now the biker starts downhill, which means his speed is proceeding from the point time 20 to speed 10 up to time 30 speed 20. So notice that has a slope, 20 minus 10 over 30 minus 20. Basically in 10 seconds, I increase 10 feet per second. So this is an acceleration of 1, a slope of 1. Again, the graph is kind of not drawn to scale, so I could squeeze it in here because I just drew this myself. But let's look at this third phase from 20 to 30. Super cool. So slope, which is 30. I kind of forgot. 20 minus 10 over 30 minus 20. 20 minus 10, which again is meters per second, over 30 minus 20, which is seconds. I end up with 10 over 10, or 1 meter per second per second. I'll write it this way this time. Well, that's my acceleration. So I have a constant acceleration again. Yeah, he's accelerating. Of course he is. And notice it's positive. He's increasing his speed from 10 to 11 to 12 to 13 all the way up to 20 feet per second. And he's going to stay at 20 feet per second. So my velocity, I'm just using the formula this time, is equal to acceleration times time plus my initial velocity. So didn't I just figured out that the acceleration is 1? What's the initial velocity? Again, it's the initial velocity in this time frame, not clear back to the start. What was my velocity when I started this whole thing? When I started that time frame? Wasn't it 10? Does that work? Is that right? Got the same worry that
Do you
I had.
still run into the problem with a different starting point?
Yeah, this is the same problem as before. In other words, if I say, okay, great, there it is, I got it. There's my velocity equation. Well, if I'm at 20 seconds, in other words, v of 20, this formula would say then your speed is 30. All right? At 20 seconds, is my speed 30? No, it's supposed to be 10. So again, you can't just stick that in there as though that's your initial velocity. You've got to make sure that, well, you need to make sure that v of 20 is equal to 10. So it's not that simple. It's very tricky. So this doesn't work. What does work? Yeah, v equals t plus initial velocity, but I need v of 20 to be 10. So that means 10 would be equal to 20 seconds plus v0. Oh, if I subtract 20 from both sides, v0 is actually equal to negative 10. So my equation is v equals t minus 10. because we're not at time 0. That's why this doesn't work. That's why you can't just throw that 10 in there, because that's our initial velocity, but that's not at time 0. I need the initial time here to be 20. That's why I can't just throw that in. So now I've got my velocity equation. Let's just check and see if it works. If I put it in, I got to speed up, we're about out of time. If I put it in 30, do I get 20? Like, is it working? If I stick 30 into my equation, do I get 20 out? Yeah, I do. 30 minus 10 is 20, it's working. Let's take the integral of this. The integral of t is t squared over 2. The integral of 10 is 10t plus my initial position. But again, that's not the position at time 0. Isn't this my initial position? The finished position from 5 to 20 becomes the initial position from 20 to 30. So I need S of 20 to be 175. So I'm not going to take, I need S of 20 to be equal to 175. So, okay, that means 175 would have to be equal to 20 squared is 400 divided by 2 is 200. 20 times 10 is 200. So I need whatever S0 is for that. Hey, look, those cancel out. So that means S0 is 175. Sort of got lucky. So that means my position equation is 1/2 t squared minus 10t plus 175. Cool. And so now I can use that to figure out my final position. In other words, my position at 30. When I do that, if I don't choke, I get 325. So again, this is your final position, which is at time equals 30 seconds. And last, then, this fourth and final segment. Notice the speed is 20 the entire time. Let's go fast here. So it's 20 the entire time. So that means the acceleration is nothing from 30 to 60 seconds.
Because it's just a triangle, sorry, because it's just like a integral, and that's just the area. Can't you just find the area of the rectangle and say, just add 20 times 30? And there's your answer. So 325 plus 600, you get 925 meters.
That is exactly right. Yep, because we're talking about areas under curves here, and we literally have a curve. So that's an outstanding observation. So in this case, position, let's just quickly do this, would be 20t plus the initial position. If I get this involved, then that means I need 325 to be equal to 20 times 30 plus S0. The only way that works, since 20 times 30 is 600, if I subtract it to both sides, is if S of 0 is negative 275. So that means my S equation would be 20t minus 275. And so now I can find my final position, S of 60. When I do that, as Daniel said, you get 925. So that's how far he actually travels, 925 feet, if I needed to know that. And yeah, isn't the area under the velocity curve, if you multiply velocity, which is feet per second, times the height, which is in seconds, then don't those cancel and you get feet? So the area under that curve. So because this is just geometry, if you found the area, I'll erase this, but I guess I don't need to erase it. If I found the area of that triangle and add it to the area of that rectangle and add it to the area of that trapezoid and add it to the area of that rectangle, I'd get 925. Excellent observation. Now this problem actually asked us, let's just do this really quick. It actually asked us to find the graphs of S of t and A of t. And so the A of t graph is fairly easy because it was constant the whole time. Like for the first phase, it was 2, and then it was 0, and then it was 1, and then it was 0 again. So wouldn't the acceleration graph, acceleration is a function of t, how did I word that? And notice the important things here are the stopping points from 0 to 5, and then 5 to 20. Don't have to draw this to scale, and then 20 to 30, and then 30 to 60. It was 2 the entire time from here, and then it went to 0, and then it went to 1, and then it went to 0 again. So it's like this would be the acceleration graph as a function of time. Does that make sense to you? Now the position graph is a lot more complicated than this, and it's actually really nice to go into Desmos and try to set up. I'm going to do that. I'm afraid it's going to take too much time, but let's just at least think about this. I think maybe I'll graph a good one for the notes, but let's just stare at all the different position equations. So my first one was a parabola. So it's a parabola from 0 to 5. And then what is it in the second phase? Then it's a straight line, parabola, then it's a straight line, and then it's back to a parabola again. And then it's back to a straight line again. Let's take a look at that. Again, feel free to leave if you need to leave. I think I can do this pretty fast, but. So our first equation.
Yeah, I gotta get going. Bye.
See you later. I'll make a graph of this quickly so it's in the notes. So you have, I wonder if I can use the regular letters. S equals T squared. Yeah, we can do that. And we've got to limit that only to go from T is 0 to 5. Very nice if I could use the copy feature. I can't do it in this app though. So from 0 to 5, that's what this thing looks like. I'll kind of expand it out a little bit so it ends up looking better. And then it jumps to 10t minus 25. So S, capital S. S equals 10t minus 25. And what's important about this is you'll notice it picks up right where the other one left off. That's what's important about this. That's why we had to get that initial position right. And then that thing exists between 5 and 20. So 5 is greater than, t is greater than. Come on, idiot, where's t? There it is. So it starts out as a parabola, then it cruises as a straight line. Now it's going to pick up as a parabola again. That third parabola is a little more complicated. It was S equals 1/2. I'll type 0.5 times t. Should be using x to be going faster. T squared minus 10t plus 175. Again, super cool that it picks up exactly where the other one left off. And this existed between 20 and 30. So I'm going to go and throw parentheses into that and say I want this to live between 20 and 30. Boom. It's almost impossible to graph these by hand and have it look good. So notice the transitions are smooth. It's really kind of cool. And then lastly, it was a line, 20t minus 275 for the remaining 30 seconds. So, S equals 20t minus 275. Minus 275. Awesome. It picked up right where it was supposed to. And then this existed from 30 to 60. So 30 less than or equal to t less than or equal to 60. Close the parenthesis. Bam. So there's our S versus T graph. And there is actually a way to go in here and label the axis. My x-axis is time, and my, I'm going to be a capital though. It's time. Come on, man. And my position is S. Has a function, parentheses of t. Sweet. So now I've even got a label on there, and so that's kind of cool. So it's continuous motion, but there's 4 phases to it. That's just kind of neat. And notice you can actually see the 925 happen in there, even though I didn't stick it on there, but that's kind of cool that you can. Stick that in notes. Just you and me, Evald. How you doing? Is this functioning for you?
I mean, like for one question, that's a lot of work. There's a lot of places you can make a mistake.
Yeah,
but
sure.
Desmos, it's nice that you can check your work by just, graphing basically the distance.
Yeah, that's exactly right. So there is a lot of things you can think about, but you're right. It'd be really easy to make some kind of a goofy mistake on this, that's for sure. Shoot, all that work to make S of t and it didn't even show up there. So I'm going to write it in. S is a function of t. So it's kind of cool just to add these in here too. I'm going to go ahead and throw these in. So at time 60, this was at 925. If I wrote this down some other place. Oh, I guess I got it here. It was at 925, and then it was at 325. So that looks like that works. At 30, it was at 325, and at 20, it was at 175. And at 5, it was at 25. I remember right. I think that was all of them. So it's kind of cool to see the smooth transitions. But yeah, you're right. This is really tricky.
And this looks like a test question, no?
Yeah, I'd say it does, except for maybe not as many phases, because maybe like 2 or 3 phases or something like that. And obviously partial credit if you screwed something like that up. But yeah, I'd say that's true. Yeah. Something to think about. All right.